Hello everyone, and welcome to the second video of the first lecture for the course on metric spaces. Last time we defined a distance on the plane. So we had R2, which is the plane, and we said that for any 2 points P with coordinates xp, yp, where xp is the x-coordinate and yp is the y-coordinate, and point Q with coordinates xq, yq, the distance between P and Q, which we said we denote dpq, is given by the square root of xq minus x p squared plus yq minus yp squared. In this lecture, we want to understand what can we do with a distance, which constructions we can perform. Now, just as a definition, and basically it's a name, R2 with the distance we defined is called a metric space, thus explaining the name of the course. Clearly, there is a much wider generalization of the notion of a metric space, which is any space with a distance. We're not going through the details here, but R2, the plane with this distance, is an example of a metric space. Now, we've got this distance and we've already computed the distance between 2 points. Now, something which might be natural to do once you have a way to measure the distance between 2 points is ask yourself, which points do I have near me? By which we mean which points have a distance from me which is smaller than a fixed number. So let's say we fix a distance of 1 around us. Which points satisfy the inequality dpq smaller than 1, where p equals 0, 0, for example, is our position? Well, to see which points satisfy this inequality, let's impose the inequality, which means dpq, which is equal by the formula we have here, to the square root of xq minus 0 squared plus yq minus 0 squared, which is equal to the square root of xq squared plus yq squared, must be smaller than 1. Now recall that if you have the center of a circle and you define and you want the circle with a given radius, then the equation of the circle with center in 0, 0, which is our initial position, and radius 1, is given by x squared plus y squared equal 1. Therefore, if we draw the picture of the y-axis and the x-axis, and we take the point 0, 0, and we decide that here it's 1, 0, then here there will be 0, 1, here minus 1, 0, and here 0, minus 1, then the circle of radius 1 and center in 0, 0 is this circle. Now, the inequality we were imposing is that the square root of the sum of the squares x squared plus y xq squared plus yq squared is smaller than 1. And here we are saying that this purple line has equation x squared plus y squared exactly equal to 1. Therefore, the points satisfying this inequality are exactly the points inside this circle. So if we were in 0, 0 and we wanted all the points whose distance from us is smaller than 1, then we would get all the points inside this circle. Be careful, only the one inside the circle, not the ones on the boundary, which is exactly the circumference whose radius is 1 and whose center is the point 0, 0. This is a general construction we can perform when we are in a situation in which we have a distance. Say we take a point P in the plane, that in this case doesn't have to be 0, 0, as in the previous example, and we fix a radius r, which is a real number, positive. Then we can ask ourselves which points have distance from P smaller than r. And these are exactly the points that we denote with B, PR, and this is exactly the ball centered at P of radius r, and these are all the points Q in the plane such that the distance between P and Q is strictly smaller than our fixed radius r. So if we come back to this example, then the points inside this circle coincide with the ball B 0, 0, 1, which are exactly the points that have distance from 0, 0 at most 1. What we want to do now is to define a new metric on the plane and see what balls are in this new metric. So we want to define a new distance on the plane. How do we define it? Well, we take 2 points, P equals to xp, yp, and Q equal to xq, yq, and we define the distance between P and q to be the sum of the absolute value of xp minus xq plus the absolute value of yp minus yq. Recall the definition of the absolute value, which is if you have a number r, then the absolute value of r is equal to r if r is bigger or equal than 0, and to minus r if r is smaller than 0. So for example, the absolute value of 3 is 3, while the absolute values of minus 3 is minus 3, which is 3 once more. Now, this metric, or distance, is also called the taxi metric. The reason why it has this name is that if you picture yourself to live in a city where all the roads are in a square grid, so this is the x-axis and this is the y-axis, and this is a road, this is another road, this is another road, and the same thing vertically, one road here, one road here, one here, and you want to start from this point P, and you can only go via the roads, and you want to get to Q, then you would have to go this way, then this way, then you could either go up or right, and then right here. And if you want to measure the distance between P and Q, you have to measure the length of this part here, then the length of this one, of this one, of this, and this one. So if you were driving in such streets, then it would be very helpful to measure distances using this metric here. Our aim now is to try and draw the ball centered at 0, 0 of radius 2 in the distance given as above, by which we mean we have to take the distance between 0, 0 and a point P, which has coordinates xp, yp, and then this distance is given by the absolute value of xp minus 0 plus the absolute value of yp minus 0, which is just absolute value of xp plus absolute value of yp, and this must be smaller than 2. We have to find all the points that satisfy this inequality. Well, this inequality has different meanings depending on where we are in the plane. So let's write down the various meanings of this inequality respect to the positivity and negativity of the two coordinates we have here. So if we are in this quadrant here, where the x's are positive and the y is negative, then the inequality is given by xp, sorry, also the y's are positive, then xp plus yp must be smaller than 2. In this quadrant here, where the x's are negative and the y's are positive, the inequality becomes minus xp plus yp smaller than 2. In this quadrant, both y's and x coordinates are negative, so the inequality is minus xp minus yp smaller than 2. And finally, in this quadrant, where the x-coordinate is positive and the y-coordinate is negative, we have the inequality xp minus yp smaller than 2. Now, it is much easier to draw the line where we take equality rather than inequality, and then decide on which side of the line we have to take the points. Now, the line with equation xp plus yp equals 2 is the one that goes through the point 2, 0 and the point 0, 2 and connects them. So it's this line here. In the same way, the line minus xp plus yp equals 2 goes via 0, 2 and minus 2, 0. So it's this line here. The line minus xp minus yp is equal to 2 goes via minus 2, 0, 0 minus 2. So it's this line here. And finally, the line connecting x of equation xp minus yp equals to 2 goes via 2, 0 and 0 minus 2. So it's this line. As I said, these points are 2, 0, 0, 2, minus 2, 0, and 0 minus 2. Now, if we take the point 0, 0, which is this one, then it is true that 0, 0 is smaller than 2. So this point, this side of the line, is the one where xp plus yp is smaller than 2. In the same way, 0, 0 satisfies this inequality, and this inequality. So the points in this square are the ones that have distance from 0, 0, at most 2, and therefore the yellow part is exactly given by the ball centered at 0, 0 of radius 2 for the taxi metric. In the next video, we will go through some other examples of distances on the plane, showing that there are other examples that behave differently from what we would be used to expect from a distance. See you in the next video.